over here. Come on in, because there's going to be other people that come in late. So come on in over here. Yeah, that's perfect. Thank you so much, guys. You can sit right down there. That's great. Thanks, guys. Okay, so you're recording? You're recording, Jack? Okay, let me know when you start. Good? All right. Well, ladies and gentlemen, we're going to get going. Thanks so much for packing in. I know it's a tight classroom space. So we're going to go through the strategic design workshop. I've given this workshop a couple of times in the past, and hopefully this is something that your team can use for this coming season. I want to start off by just talking a little bit about who I am, just so you guys have a little bit of my background. I'm one of the lead mentors on 1678 Citrus Circuits. I'm also, my day job is a mechanical engineer for a company called SunPower. I make robots that clean solar panels for SunPower. I lead that engineering team. I'm going into my 16th season involved in the first robotics competition. I was on team 114 out of Los Altos for about 4 years, freshman through senior year of high school. And then I came to UC Davis and started mentoring 1678 in 2008. And the last thing I want to say is I swear I'm not a really smart guy, okay? And a lot of the ideas you're going to hear in this presentation are not my ideas, okay? But I have a rule for that, and you'll get that in a little bit. But I just want to let you know that there are a lot of really smart people in this program, Karthik being one of them. We have a great team right next to us, being 254, with just a wealth of knowledge. And a lot of the information you'll hear today is kind of pulled from those sources. So let's go a little bit overview of what we're going to talk about. I'm going to try to keep the presentation to like 45, maybe 50 minutes so that we have some time at the end for questions. So if you have questions, hold them at the end. We'll have time. Maybe write them on your notepad or take a note on your phone if you have a question, and we'll get to it at the end. We're going to go through some preseason prep, things that you can do in the preseason to leverage your resources and be prepared for the build season. We're going to talk a little bit about drivetrain design, but only on a very high level, and the things that you can do as a team to guarantee that your drivetrain is in good shape for the event. We're going to talk about mechanism design for a little bit. We're going to go through some of the key things to think about when you're approaching mechanism design. We're going to just note electrical pneumatics very, very briefly, things that you should be making sure you're doing in those regards, as well as programming. And then we're going to talk about how to structure an effective build season and how to structure an effective competition season. So let's talk about preseason prep. Golden rule number one, we're going to have 5 golden rules. Golden rule number one is keep it simple, all right? The biggest thing that you can do to have a great season is to build within your team's capabilities, okay? I have a picture of a rookie team we started a couple years back in Winters. This was their robot from their rookie season. It had a low goal scoring, I think it had the gear intake. Which year was this? But it was just kind of a tank of a robot, but it did a couple things and it did them well, and they had a really great season doing that. And I think a lot of teams can share similar stories of the times where they decided to build simple and within their resources. So simple robots also tend to be robust and effective. And then the last thing I'll say with regards to this is 1678 firmly believes in a function over form philosophy. We would much rather spend an extra day making the robot work better than look better. Okay, and you'll see that in 1678's robots. They often aren't the prettiest at the ball, but they are effective robots, and we prioritize that intentionally. Okay, golden rule number 2. This is another one to keep in mind all season. Steal from the best, invent the rest. Okay, what this means is, there are a lot of other teams that have already solved a lot of the problems that you will solve in a given season. Okay, so rather than working in a vacuum and with your eyes and ears shut to the outside world, keep your eyes and ears open. We'll talk about that, but doing research about what the rest of the competition is doing is super important. If you're not doing that research, you're missing out on a myriad of resources. One of those that I'm a big fan of is the Robot in 3 Days programs. This is something that started in 2013, and it's gotten so huge. There's like a dozen plus Robot in 3 Day teams that are all over the world. And the great thing is they're uploading YouTube videos starting kickoff day. And they're uploading some of them upload like hour-long videos, 2-hour-long videos of their process. And the reason why this is so valuable is it's basically like maybe your team has 10 kids, maybe your team is bigger, has 30, 40, 50 kids. you have a certain amount of kids that can work on prototyping, but you have a limited number of resources. Every team is limited, right? Robot in 3 days essentially multiplies your prototyping resources, right? It's all these people that are solving some of the same problems you're solving all around the world, and you can get a ton of information from that, but you have to be ready to do your research every season. So don't stick your head in the sand. Keep your eyes and ears up and look around and see what everyone else is doing. See what the community's posting online and learn from that. And then also in the preseason, a great thing that you can do is study some teams that year after year build simple robots but compete at a very high level. Okay, they're not the flashy blue and black robots that we're used to seeing out in the field doing everything, but they build robots that are built robustly, simply, not a lot of bells and whistles, but they get the job done. 2056, 610, 973, 330, they're all great examples of teams that build simple robots that get the job done. They forego a lot of these features that some of us can get caught on. Oh, we need to be able to score backwards. Oh, we need to be able to pick up from both sides of the robot. I mean, these are things we can convince ourselves that we need, but then when push comes to shove, the team probably doesn't need to do that feature or that ability, and you can get away with a simpler robot. And these teams really exemplify a lot of those decision-making processes. So those are great teams to study and learn from. Simple, effective robots. Okay, this is another thing that you should be doing now and for the rest of the preseason is learn your FRC history. Okay, be a little bit of not just an engineer, but a historian. Okay, there are many games which will have elements that are repeated from years prior. Okay, this is a great example. Here's a picture of a 2007 robot scoring a game element. And then here's a picture of a 2011 robot scoring a game element. You'll notice the objects look very similar. And actually, you can even see there's 3 levels of scoring that look oddly familiar, okay? It was almost a repeat game as far as the tube scoring went. So teams like ours, for example, 1678 in 2011, we actually, when we saw the game and we got to the prototyping stage, we went back and we saw a picture of Team 100's intake from 2007, and we found a great side view picture of this, and then we projected it onto a piece of sheet metal and traced out the geometry, and then just cut that with a jigsaw and a hole saw, and then we had our intake for 2011, right? I mean, it was just like copy paste, steal from the best, invent the rest sort of stuff, but we knew what they had built in 07 because we remembered that game was very similar to 2011. Things like climbing, it feels like every other year now you have to climb up a bar, right? We did it in 2016. We climbed up rope last year. We climbed up a bar this year. So there's a lot of lessons that you can learn from past years. So make sure you're studying past games, exercise balls, foam balls, even Frisbees in 2013 remember the plastic gears in 2017, the yellow ones? It turns out that Frisbee intakes from 2013 actually worked pretty well on gears. So when we got the game challenge, one of the prototyping teams on the 3rd day or whatever, they headed out and they grabbed our 2013 robot, hooked it up to a battery, ran the intake, and shoved a gear into it, and it picked up the gear. And we're like, well, I guess we can build something like this. So, I mean, you can reuse concepts year over year. So really valuable to know what's happened in the past so you can steal some of the best ideas from those teams to implement in the current season. All right, off-season projects, some examples of things that you can do with your team now before the season starts. It may be a little late to do some of these things, but you can still give it a shot. I highly recommend getting some experience building a drivetrain like the Kitbot. Building bumpers, it's something you know you're gonna have to do next year, and it can take a lot of time if people don't know how to do it. So maybe you have a crew learning how to build bumpers so they're ready for the season. But then you can also try designing some more game-specific mechanisms like ball intakes or shooters, elevators, climbers. This is an example of an off-season robot that performed terribly at Madtown Throwdown, but it was an opportunity for our students to learn how to design a lot of different elements. It had like a pneumatic catapult and a ball intake and a turret. It had just a lot of different things that we had never done before, and we kind of mashed it all together in one little, and it was also a very tiny robot. You can see it's like, you know, pick it up with one person sort of thing. We were trying to learn a lot of different lessons with that robot, and so it just became a project that we knew wouldn't be super successful on the field, but we knew it would give all of our students a good opportunity to learn new skills and learn how to design new mechanisms. All right, we're booking it through this presentation, Drivetrain Design. We're just going to talk about some basic tips, but first, I want to spend some time looking at these robots. Can anybody tell me what's the same between these robots? But the answer is not that they're blue and that they're 254. Yeah. West Coast what? West Coast drive base. So it's a little hard to see with the bumpers, but you'll notice the drivetrains look oddly similar, right? Maybe the number and the size of the wheels changes, but there's always wheels on the side of their robot, okay? Poofs, every year, they build a West Coast or a tank-style drivetrain, okay? So our golden rule number 3 is use a proven drivetrain, which for 99.9% of teams is a tank-style drivetrain, okay? So if you're sitting in this room, you should build a tank-style drivetrain, okay? And the reason being, well, I mean, there's a lot of reasons, but think about it this way. If it's good enough for a team that's won 4 world championships in the last 7 years, it's probably, or last 8 years, it's probably good enough for your team, right? That's the way that we've been thinking about it. I mean, it's like, it's not even a discussion on our team. We don't even spend any time talking about it in build season. I'll go through that in a little bit. Just a basic 4, 6, 8-wheel drivetrain. Sometimes you need to make them big pneumatic wheels to climb over objects. Sometimes they can be smaller wheels, or like the Andy Mark Kitbot is awesome. I love it. I'll talk more about it in a little bit. Team 1114 has some good resources on how to upgrade your Kitbot a little bit, make it a little more robust. The best thing about the Kitbot is you can build it in a weekend, and then you can spend the whole rest of your build season designing the best mechanisms. Because to be honest, the drivetrain does not win you a competition, all right? It's the mechanisms that win you a competition. The drivetrain can only lose you the event, okay? You try something new, you try a mechanism, you try a swerve drive, and it works terribly. And then it doesn't matter what you have on top of the robot, you're gonna be losing that regional, okay? You build a simple drivetrain that you can build in one weekend, and then you move on to the things that are actually gonna win you matches, because it's not gonna be your drivetrain. This is probably one of the biggest mistakes that FRC teams make year after year. There's students on the team that want to do fancy drivetrains. They want to do their own custom West Coast. They want to do their own swerve drive. They want to do a mechanism drive so they can drive sideways. All right, and then they end up falling flat in season. And and not only do they not perform well, but they end up spending weeks upon weeks of their build season designing a drivetrain that they could have just bought from Andy Mark and built in a weekend. Right? And this goes into this whole strategic design. What's the most valuable, what's going to get you the most bang for your buck? It's not spending a month designing a custom drivetrain in build season. You're not going to get the value that you invest. You're going to get the value from spending a month designing mechanisms and spending a couple hours on a weekend building your Kitbot. So I highly recommend, if you're a rookie team, if it's your 20th year in FIRST, build the Kitbot. Build the Kitbot. And we're going to go back to this again. Please build the Kitbot. Here's an example of when a team that you may recognize the number of did not follow this advice. This is 2008. This was 1678's robot for the 2008 competition. That year you got a couple points for doing laps. And so they decided to build a lap robot. But they're like, what's faster than a normal robot? A robot that looks like a car. So they have this like steering wheels in the front and only one wheel with like 6 sims on it on the back, right? And they thought they would be like the fastest robot in the competition. Well, they also happened to strap the battery like 1.5 feet off the ground. And so every time this thing turned corners, it would roll over. I mean, it was just like, it was a terrible robot. They should have just built the Kitbot. Even if they made a lap bot with the Kitbot, it would have been better than this, okay? And you can ask anyone who's on the team then, it was like, yeah, that was a big mistake. But this is an example of someone thought we had to make a better drivetrain because that's what's going to win us the event, and it wasn't true at all. All right. If they would have built a simple drivetrain, they could have moved on to other things, or even just driven it and found out that, oh yeah, our robot does roll over when we turn, and built something a little lower to the ground. So don't do what 1678 did in 2008. Build a standard tank drivetrain. Use the Kitbot. You'll thank me later. All right. Mechanism design. Let's talk about mechanism geometry really quick. This is very high level, things that you want to keep in mind. Now that you've already decided you're going to use the Kitbot, because every team should, okay? You're using the Kitbot, you're building a very simple drivetrain. Now you got to think, okay, what's going on top of that, right? When you're thinking about your mechanisms, a couple things to keep in mind. Try to simplify everything, right? Keep things as simple as possible. And a big way to do that is by minimizing degrees of freedom. I have this robot up here as an example of what not to do. This is 971, probably one of the most technically competent teams in FRC. They had that crazy arm this year. 2016 was a great example too. They had a pivot here, and like if they did things wrong, the intake could hit the shooter. It was all sorts of crazy nesting going on. This is an example of many degrees of freedom and much complication, okay? You want to be the opposite of what this is. You want as few degrees of freedom, basically as few moving parts as possible, because it's going to simplify your entire build process. So when you think about, do you really need to have a double jointed arm to reach up to the top, or could you do it with a single joint and you just have the claw rotate rather than pivoting on its own? Or could you really do that with, do you really have to have 3 stages of your elevator, or could you just do 2? Right? Think about these things and try to minimize the complexity of your mechanisms and keep it as simple as you can. A low CG is super important. We just talked about with the rear cab, but keep all your batteries low, keep your electronics low, as many motors. The motors are the second heaviest thing outside the battery, so keep those as low as you possibly can. We like to design things to be symmetrical. This actually is nice from a symmetry point of view. It's you got rails on both sides. It's built almost like a mirror image. Keeping the symmetry when possible is great. Another important aspect is staying inside your frame perimeter. So a lot of times, you see teams that they're super excited about this intake they made, right? But they didn't maybe make it as robust as they could have, and they're using it, it's working great, and then they run into a wall, and then the whole robot crumbles into pieces, right? So it's really important that you keep as much stuff of your robot inside your frame perimeter during the match. And if you do have to reach outside the frame perimeter for an intake or for scoring, either make it super robust by being very solid, so if it gets hit, it doesn't break, or make it super robust by being super flexible, so if it gets hit, it flexes out of the way. Those are both options, but just know that if anything's coming out of your frame perimeter, it will get beat up, and you have to be ready to make it robust and test it against walls and stuff like that to make sure that it's not breaking. Okay, let's talk just real quickly. There's 2 options for movement. You got motors and you got pneumatics. Motors give you a range of motor choices, a range of power options. You can use gearboxes to reduce to whatever torque you need, all that jazz. They allow for a lot of variable movement. So this robot in 2014 that was able to move its claw to really any shooting and pickup angle they wanted to, because it had motors doing a variable rotation. So they're great for that sort of stuff. They're harder to control. You need sensors and some feedback loops to control them accurately for a lot of things that motors are doing position-wise. But that's gone a little bit easier with the Talon SRX and mag encoders. So I highly recommend using those if you aren't already. They're a little, they're an investment, but at the same time, they work super well and they make this whole process a lot easier. On the flip side, from motors, which can be more complicated, you have pneumatics. And pneumatics can be a lot simpler because all they really do is go point A to point B, right? Pneumatic cylinders, here's a couple that are here. Actually, there's quite a few on this robot, but they're either out or they're in. And so that makes it great for a couple applications, like when you need something to just be super repeatable, you can do it with pneumatics. The downsides of pneumatics are you need either a compressor or a whole lot of air tanks to have air for the whole match. The way that you need to design pneumatic systems is to minimize the amount of air use. So if you have, example is, if you have a mechanism that you're going to be using all match, it's probably not a good fit for pneumatics. So teams will make the mistake of they'll use a massive air cylinder to raise and lower an arm on their robot, right? And then they lift their arm up twice, bring it down twice, and they're out of air for the rest of the match, right? So maybe that application, motors would be a better job, but or do a better job at that. But for things like this robot, for example, it used pneumatics for its climber, so you actually can't really tell, but it's actually a couple inches off the ground right now. But you only climb at the end of the match. It's like a one-time deal, right? So at the end of the match, they just raise the hooks up, grab onto the bar, suck the hooks back in, and then they're climbing, right? And so that's an example of a good application for pneumatics. It's something that you need to be very simple, repeatable. You're only doing it once, so you don't have to worry about it using a ton of air, and you need to have a lot of air tanks on your robot at that point. So that's a good application for pneumatics. Another great application example is on 1678's Climber this year, there was this ramp on the side of it, and there was a hook to release the ramp and have it flop down. That was a perfect application for pneumatics. It's just a small cylinder. It just has to fire once at the end of the match, so it's not going to use up a lot of air. And it's very repeatable and simple. All right, we're going to talk about game object processing. So again, this is a very high-level talk, right? So we're thinking high level, what are the priorities I need to balance when we're designing mechanisms, okay? With game object processing, I want to go through some examples of places where teams can maybe not think through the whole process and miss some important aspects of game object processing. So acquisition manipulation, storage, elevation, positioning, and release. These are all things that you have to think through when you think about, like, for example, I need to pick up a tube. How am I going to acquire the tube? How am I going to manipulate and store the tube once I have it? How, like in the case of 2011, how am I going to lift the tube up to the scoring locations? How am I going to position it once it's in the scoring like height? How am I going to make sure it goes onto the scoring object? And then how am I going to release the game object at the end? These are all important steps to think about when you're thinking through any sort of mechanism design. Am I thinking about the game object throughout the whole process? And here's some examples of times where people aren't thinking through the whole process. Maybe 2013 is a good example. 2013 was a Frisbee shooting game, okay? There were these slots, kind of like a printer machine slot, or like a mail key slot, where you could slide Frisbees out into the field through the slot. And that's how the human gave the robot Frisbees. Now, every team was like super stoked to build a Frisbee shooter, right? So every team's building these shooters, and they're shooting the Frisbees super fast into the goal, and they can shoot the Frisbees that are in their robot perfectly, right? They start out with 3 in the match, they shoot them in autonomous, okay, awesome. But so many teams did not think through the acquisition step. So they got this awesome shooter, and it's got this Home Depot bucket to like as a hopper kind of for the Frisbees, but they haven't thought at all about how the human player is going to slide the Frisbee through the slot into their hopper, right? And so you see these teams, they shoot their three Frisbees, they're stoked, and they drive over to the wall to get more Frisbees, and their human player is like, they got the Frisbee, and they're like very slowly pushing it through the slot and praying that it like drops and does a flip and lands perfectly in the hopper. And they would spend the rest of the match at the wall just waiting to try to load one Frisbee up, right? And it wouldn't work because why? Because they didn't think through the whole process. They were good on storage and they were good on release, right? But they had not thought through how they were going to acquire the game element. And that's what bit them in the butt, right? So it's really important that you're thinking through the whole process. And here's a couple tips in that process. With acquisition, this goes back to what I was talking about with the Frisbee story. Acquisition zone is the thing you need to remember. The effective intake area. This is an example of a 2012 robot that has an intake that is the full width of the robot, right? So this entire area, it's possible for them to pick up the game element, and then it will center itself into their hopper, right? If you don't have a wide acquisition zone, it makes it exponentially harder for your driver to pick up the game element. All right, because they're often 50 feet away from the robot and the robot's driving sideways, and there's no way, if the ball is 6 inches in diameter and you make a 6-inch intake, right, there's no way that driver's going to pick up that ball. Not in a million years, all right? It'll take them all match and they may never get it, okay? But when you have an intake that's 30 inches wide to pick up a 6-inch ball, you have way more wiggle room, and it's going to increase the effectiveness of your intake, and it's going to increase the speed at which they can grab the ball, okay? Make the driver's job easy. These are things that you really want to test in the prototype. When you're making a ball, like a ball intake prototype that you know it can be like 20 inches wide, make a 20-inch wide ball intake prototype. Don't make like a single wheel roller and then just multiply that out by 20 inches. Make the full width, test it out, make sure the acquisition zone is good enough. There's been years where we couldn't, or actually, well, now I'll skip that story. Let's keep going. All right, golden rule number 4, rolly grabbers. So this is going with acquisition zone. How do you acquire the game element? Always use a rolly grabber, all right? So we talked about, what was golden rule number 1? Yes, KISS. Keep it simple. Golden rule number 2, steal from the best, invent the rest. Golden rule number 3, build a tank drive. Golden rule number 4, always use rolly grabbers. Always use rolly grabbers. What do I mean by rolly grabbers? I mean an intake where you turn it on before you're ever at the game element, right? And it just runs. And then when you get to the game element and make contact with it, the game element goes into your robot and you have control of it. This is called, 118 has a phrase called touch it and own it. Basically, if you touch the game element, you should own the game element. All right. This is in direct contrast to what some teams will make. I call it like a single intake or like a claw, something that needs to be triggered when you're at the game element to acquire it. A good example of this is in 2014, we had these big exercise balls that were probably like 40 inches in diameter, right? And some teams were smart. They had rolly intakes, so they just go up to the ball and the wheel would suck it into their claw. But some teams had these big, like, it's kind of like one of those prize machines that you go down and the claw closes and lifts up the prize. It's rigged, so you never get it. But so Well, it's kind of the same way when they're using the claw. So they drive up to the ball, they're running at the ball, right? And the guy's like, close the claw, right? And the operator has like a quarter-second delay, and the driver's already hit the ball, and the open claw is not holding on to it. It's still in the process of closing, and the ball's already 10 feet away from the robot, right? And they're like, okay, keep chasing it, and they run down another 10 feet, right? And then they try to close it again, and they miss it again, and then they used up all their air because they made it with pneumatics, and they've already used up all their air tanks. I mean, this is the stuff that you see when teams aren't using things like rolly grabbers, when they're not following those principles of making the acquisition as smooth and as seamless as possible. Because the reason why it's so important for this to be fast and easy is when you add up the time it takes to acquire, manipulate, store, elevate, position, and release the game element, that's what we call your cycle, okay? And if all of these steps take 10 seconds to do, you're looking at a 60-second cycle. And maybe you can only score 2 game elements in the whole match. Okay? The key is to make each of these steps as quick as possible so that you can score as many times as possible in that match. All right? We call it cycle time, but it's really important to minimize the time it takes because it's only a 2.5-minute match. It's not a lot of time. You need to do everything quickly. And so using rolly grabbers means the instant you touch it, you've already picked it up and you can start driving off and doing the next thing. All right, another case study. I have 2 slides to watch this time. Okay, so pay attention. Remember, the answer isn't going to be blue. Okay, given what we just talked about, what do you notice that's a similarity in all these robots? Anyone? Yeah. They're all see, he wasn't there for the first question. Yeah, back there. All use a similar drivetrain. That's great. What else? We just talked about intakes. Anyone knows the intakes? Yeah. Rolly grabbers. Okay, all but one, actually. So all these robots have rolly grabbers. Even the soccer robot had a rolly grabber. Frisbee robot had a rolly grabber. Tube robot had a rolly grabber. Rolly grabber for the balls. Rolly grabber for the exercise balls. But in 2007, the first tube year we had in a long time, they built a pneumatically actuated claw to pick up the tubes. And this happens to be the only 254 robot that didn't win Silicon Valley. All right? So the lesson is, if you want to win your regional, use roller grabbers. All right, cool. Everyone got the lesson? Yeah? All right, cool. Let's move on to the next step. All right, we talked about reducing our cycle time by making every step as quick as possible. Alignment is a big aspect to scoring, right? Especially if it's a shooting game, you need to line up properly in order to score effectively, right? And there's a lot of ways to do that, but one of the things to think about is it possible to just ram into a wall and line yourself up, okay? In 2013, for example, we had this pyramid here, and this pyramid was always in the same spot relative to the goal that you were shooting the Frisbees into. So rather than have a camera system with range detection and all that stuff, we calibrated the shooter. I was mentoring 1662 this year. We calibrated the shooter to, you can see it down here, it's at one fixed angle and at one speed on the wheel. There's actually no sensor on it. It was just run it at a certain voltage, which was really bad. Basically no sort of vision or anything like that. There were a couple of hooks that you can see pneumatics down there. There were a couple of hooks that we pull up. We call them our bullhorns. And the driver, I kid you not, would just drive full speed into the pyramid. The bullhorns would ram right into these 2 bars. The robot would stop in its tracks. And then the operator would just go fire, 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 fire. No lineup time, nothing. It's just run into the bars and start shooting because we calibrated the shot for that exact range and only that range, nothing else, right? We couldn't shoot from 2 feet further back. We couldn't shoot from 2 feet further forward. We had to be jammed into the bars to be able to score. But it was fine. You were protected when you were touching the pyramid, and we were able to shoot the 4 off real quick and go back for another cycle. Yeah. You got to wait. Yeah, I know. So these are sacrifices, right? I mean, like it's not perfect for everything, but it worked out they seeded first in Sacramento with this design. And here's another example. This is a couple years earlier, 2012. This team was like, well, you know, we could make a shooter and have to track onto these vision targets, or we could just score in the 2-point goal and ram our bumpers into the wall, right? And that worked out really well for them. So it's just an example of using the field to line yourself up and make it quicker than having to use a camera and all that stuff. All right. Let's talk about electrical pneumatics programming really quick. Just go through some stuff. Some keys with electrical. This is a 1678's 2013 robot. Do not recommend. Do a better job than 1678 did this year. It's really important to spend the time and do your wiring right, because once the robot's made and wired up, it's kind of out of the wiring team's hands and it has to work. And so you got to make sure that the core, like the backbone of the robot is solid. So spend time doing your wiring right early on in the season. An anecdotal story about this robot in particular. I mean, it's really hard to tell anything of what's going on, but if you squint really closely, you can see an air compressor over here. And there was the radio I think was over here too. And for some reason, no one even decided that it was important to strap down the compressor. So it wasn't attached to anything. It was just kind of floating. And Einstein finals match, or semifinal 3, so the tiebreaker match, the compressor shifted over and hit the wireless radio and unplugged the Ethernet, and so we were dead for half the match, and we lost that match. We could have been to the finals, but the robot sat dead on the field because we didn't spend the time to do good wiring in 2013. We got lucky that we didn't have a problem, but then it bit us in the butt on Einstein. All right, programming, really quick. This is not going to be an in-depth programming lesson. I'm not a programmer. I do not know this stuff. I'm just going to tell you right now 4 things that your programming team can do in the next 2.5 months to be ready for build season, okay? The first thing, they can learn how to write accurate autonomous driving code, okay? This usually, almost every time, uses a combination of encoders and a gyroscope, and there's plenty of example code online from other teams, including ours, that have published our autonomous driving code. And the reason why this is so critical is because every year you have to drive. Sometimes it's just crossing the line. Sometimes it's driving and making a turn. Sometimes, like this year, it was driving to the scale or driving to the correct switch. It's important to have a repeatable, accurate autonomous mode. And every year, you know you're going to have to get from point A to point B autonomously. So you might as well have that code written now in preparation for the season and have your programming team have the experience with it now and doing tests now so that when the season comes around, they can just copy pasta that code onto the robot, okay? Vision alignment. This has gotten a lot easier in the last year with the release of what's called the Limelight. It's a product that's sold by West Coast Products and designed by Team 987 in Las Vegas. It basically is a fully functional vision tracking camera that already has all of the code loaded onto it for that specific year. So they write the code to track whatever game object or vision target we have that year. And all you have to do is put the Limelight on your robot, make sure you have the most up-to-date code, and you can start tracking game objects. So this used to be a lot harder. It's gotten a lot easier in the last year. So I highly recommend checking out the Limelight if you've never heard of it before. West Coast Products should be selling it again. We talked about the Talon and the mag encoder for arms and elevators. This is important. It's basically, how do you make a mechanism that can have precision positioning, right? So like for an elevator, what you can do is your elevator can go up like a foot or 2 feet or max height. And how do you learn how to control those motors to go up and down accurately, smoothly? That's a great lesson to try to learn now. And I know a lot of teams here probably built an elevator this year, but maybe you weren't happy with the way it was programmed or was performing. This is a great opportunity to do a coding refresh because there's a good chance in the next 2 years you're going to have another elevator game, next 2 or 3 years. So it's good things to have in your toolkit now. And then lastly, have some sort of either PID or bang bang or state space or whatever, some sort of controller for a shooter wheel. Because about every other year we have to shoot something, all right? And often it's done with a wheel that needs to be controlled to a very accurate speed. So that's another important thing that if your programmers learn how to control a shooter wheel in the next 2 months, then they don't have to rewrite that code when you get to build season. They can copy that code right over and boom, you have a speed-controlled shooter wheel, okay? These are just 4 examples of things that if your programming team is looking for things to do in the next 2 months, if they tackle these 4 things, you're going to be well positioned for the build season. Speaking of build season, little overview. When thinking about your build season, I hope every team has some sort of leadership structure, whether you have president, captain, CEO, and you have sub-team leads or whatever. Make sure your entire leadership crew, including your main teachers or whatnot, sit together and talk about what your build season schedule is going to be. I'm going to go through a quick example of one, but it's important that you set a schedule and that your whole team has buy-in to try to stick to it. All right, everyone's committed to doing their best effort to stick to the schedule because they know their teammates are depending on it. I think it's really important to aim for the moon, land among the stars sort of thing. Just like aim for an accelerated schedule that's a little bit more accelerated than maybe what you had last year, or maybe you didn't even have a schedule last year, so set one. And set one that's a little difficult for you, because here's the thing, we always assume we have more time than we really do. All right, students, mentors, we all assume, You know what I mean? The robot hasn't been built yet, but we got a week and a half left in build season, and we can probably get it together by the time stop build day comes around. It's like you have to assume there's less time than there really is and set a schedule that is accelerated enough so that when things inevitably slip, which they will because we can't foresee everything, no one's perfect, you can recover from those slippages in your schedule, okay? And we're going to go through an example schedule from 1678. So days 1 through 3 are brainstorming, and we're going to hit the stop button, and we're going to go right into what it means to do brainstorming, because this first weekend is the most important weekend of your build season, okay? If you do not have a good kickoff weekend, you will not have a good build season, bar none, full stop. You need to make sure you are doing a good job on this first weekend, and it will set the pace for the entire year, okay? We have 3 steps on 1678. I highly recommend you follow the same schedule. We first do a rules test. Everybody reads the rules on our team, all right? We don't have a rules expert. We don't have one person who read the whole manual and everyone else just watched the game animation and starts building the robot. Every single member of our team needs to read the entire manual and pass a rules test before any of them can move on to the next step in the brainstorming process, okay? And if you're interested in doing this as well, which I highly recommend, 1678 will be publishing a rules test just an hour or 2 after kickoff is over. All right, so we have our veteran students who have done this a couple times, read through the rules real quick, make up a nice Google Form rules test, and we'll publish it live, and you can download it or add it to your own Google Forms docs or whatever, and then you can share it with your own team and start having them take the rules test as well. All right, it's really important you do this. So step 1 is read the rules. We have the rule test done by the end of lunch on the first day. So by Saturday at 1 p.m., almost everybody has passed the rules test. There's maybe a couple stragglers, but everyone else is done with it. And then we go to answering the what questions. What is our strategy? What is the robot going to do? Okay, that's what the what questions are. And we spend a full day working on this. So we were asking not like, is the robot going to have an elevator to lift up the tube? Or is it going to vision track onto the target to score? What we're asking here is, what are the list of basic requirements of our robot? What tasks in the game does our robot absolutely have to do? Does it have to score in the high goal, or can we score in the low goal and leave the high goal to someone else? Do we have to score 2 balls in autonomous, or can we shoot 1 ball in autonomous? List all the requirements, the whats, and not the hows. So when we're doing this exercise, there's someone who's listening to every person present, because we have all of our team members present their ideas, and they're listening. And if anyone says, so we're going to have a wheeled shooter to shoot the ball during the what section, that having a wheeled shooter is how you're going to do it, not what you're going to do. And so we have someone with the buzzer and buzzes them and says, you can't talk about mechanisms. You have to only talk about strategy, okay? So that's a really important step in the process. And when you're done with the what section, okay, which for 1678, just to give you an idea, we're done answering the what question by noon on Sunday. Okay, by noon on Sunday, we have an answer for what our robot will do for the whole season, all of the functional requirements. And they're going to look something like this, okay? This is a list we had from 2016 where we had kind of in general what's the robot doing. It's going to be able to score in the high goal. It's going to be able to go under the low bar, which was a thing in 2016. It's going to be able to cross over the A, B, and D defenses, but notice we're not crossing over. We're only crossing over the C from the courtyard. So it was like going backwards over it. It was a lot easier than going the other way. Notice we said auto needs to be able to do a 2 ball from the low bar and a 1 ball from other defenses. These are all functional requirements. What is the robot going to do match to match? These are things the robot had to do. What we're going to do in teleout: score in the high goal from the batter, which was close up, and from the outer works 1, 3, and 4. Challenge the scale, climb the scale. Shoot over. Oh, this was important too. Our robot that year had an elevator on a shooter on an elevator because we thought we had to be able to shoot over a defender. Okay, so you spend your time coming up with a functional list, and then that list is set in stone, and that is the best thing you can do. All right, and I will say one other thing about this. Just as important as making a list of what your robot will do is deciding the things that your robot will not do and sticking to that list. So things like, we are not going to score in the high goal. We're only going to score in the low goal. And you guys should be excited every time you decide not to do something, okay? Because every time you decide not to do something is like getting back days of your build season every time. You're like, we're not going to shoot in the high goal. And everyone should be high-fiving like, yes, simpler robot. Yes, all right? Get excited about that stuff because having a robot or trying to build a robot that does everything will do nothing. Nothing well, at least. Nothing worth being picked for. Okay, so then we answer the how questions. So from like lunch on Sunday until lunch on Monday, the kids are coming up with ideas on, now that we have our functional list of requirements, let's design a robot towards those requirements. What sort of ideas can we come up with? And the goal for answering the how questions is, how is the robot going to carry out the functional requirements that we listed out? And then at the end of lunch on Monday, we should have a rough idea of the type of mechanisms that we want to prototype. And that's our goal for the 3-day kickoff weekend. We want to get to the point where we have a list of functional requirements with the what questions, and then a list of prototypes to try out with the how questions. All right, so we've done brainstorming days 1 through 3. It was that 3-step process we just went through. Next, we're doing drivetrain design. So Citrus Circuits, we have our drivetrain fully designed and CAD'd with drawings done at the end of day 3. Okay, and you're thinking, wow, maybe that sounds a little quick. Yeah, it is quick. And the reason why is because right after that, day 4, we can start fabricating our drivetrains, which means that we have a whole fabrication team, and they can start making parts right away on the CNC routers and the mills and the lathes. And the robot's starting to come take shape by day 4 is when it starts, and day 14 is when the drivetrain's done. So we commit to having every year, you can count on our drivetrain CAD being completely done by the 3rd day of build season. Okay, and then we're doing our electrical layout. We're prototyping mechanisms for those 2 weeks. We're writing code for the expected mechanisms. So we have our robot programmers getting an idea of what the robot might look like. So like things like we just talked about, doing shooter wheels, elevators, stuff like that. And they're pulling in those pieces into the code base and making sure it all jives together before a robot's even built. Yeah. Well, yeah, that's great. So we do not use the kitbot, but that's because we have the resources to have a drivetrain design day 3, right? Most other teams do not have those resources. Yeah. 12. Okay. 12 students. I'm the CAD mentor, but I don't CAD anything. I'm the only design mentor on the team. Okay, so day 14, we have the drivetrain finished and assembled, and then that gets handed off to electrical, who wires up we build 3 robots, and I'll go over that in a little bit, and all 3 robots, the drive bases are built and wired up and driving by day 16, which is the 3rd Sunday, 2 weeks after kickoff, okay? During around days 8 through 21, so the 2nd and 3rd weeks, we're building the mechanisms. So this means that the mechanisms are slowly getting out of the prototyping phase and into the design phase, and then out of the design phase and into manufacturing over those couple of weeks, okay? And the programmers are starting to program those mechanisms, but they're also programming autonomous modes with the drive base because we already have the drive bases done. And then the 4th week is spent doing a lot of integration of all these different mechanisms that we've been designing, wiring them all up, and then testing the code with an assembled robot. All of this leads to the end of 4 weeks where we should have our robot finished. All right, 4 weeks. We give ourselves 4 weeks to design, prototype, build, fabricate, wire up, and program a robot. All right, because we need to start testing as soon as possible, because everything is going to go wrong when we start testing, and we know it will. So we better get it out of the way as soon as we can. Okay. And that leads us to golden rule number 5, which is fail faster, okay? Fail faster. Every time your robot fails in your shop is a moment to celebrate, okay? Because that's one less way that your robot will fail on the field, as long as you fix the problem, okay? You need to have the time to fix the problem. It's so important that we spend the next 2 weeks of build season testing, breaking, fixing, and then testing it again, and then breaking it again, and fixing that, and then testing it some more and breaking it again. If you haven't broken your robot in at least 20 different ways before you put it in the bag, it's going to break 20 different ways at the competition, okay? And then this gives you time to do driver practice. A good driver, 9 times out of 10, is going to beat a good robot. So you're not going to have a good driver if they haven't even touched the sticks until the practice match at your first regional. You will have a good driver if they spent time driving the robot the last 2 weeks of build season. Okay? There's some things I like to do in these 2 weeks of breaking and iterating. I'll intentionally try to break the robot. I mean, I'll kick it. This year, there were these ramps and stuff like that, and I would just take the robot when it was off, and I'd run full speed with the robot at the ramp and just let it go and watch it fly across the ramp, right? The robot's getting some air. The kids are crying because I'm breaking the robot, but it's awesome, right? Because we find all the ways that it's going to break in the match, and we try to fix them. It gives your programmers time to iterate their code, write better autonomous modes. All of these things can happen if your team is super disciplined and super focused on building a robot quickly and using your resources wisely so you can be done by day 29. Yeah? We try to. So yeah, that's a good question. So next slide, I think. Oh wait, was there not a picture of the 3 robots? Yeah, I'll just go really quick. So here's 3 robots, right? They're all somewhat identical, but not quite. And designing is iterative. So we're doing all this testing, breaking, fixing, iterating. But when we find a problem, we try to fix it on one robot first, validate that that fix works before we implement it on the other robots. For the record, I do not recommend your team builds 3 robots. Please don't take that away. We'll talk about that in a little bit. Competition season, because this is where we'll talk a little bit about practice robots. One thing to know, there's a myth in FRC that your build season is 6 weeks. It's just frankly not true. The build season never ends, okay? And I'll explain why. You have this thing called the withholding allowance. Hopefully you're aware of that if you've read rules before. If you're new to FRC, welcome. There's a bag day, but it doesn't mean a lot, okay? The robot goes in a bag, but you can work on whatever you want outside of the bag, which means that you can continue to design mechanisms, you can work on autonomous codes, and you're even allowed to bring 30 pounds of custom parts into the event with you. So you could bring an entire mechanism if you wanted, as long as it's underneath the 30-pound withholding limit. It's not something that you should really rely on. Hopefully you put a functional robot in the bag, okay? If you follow the plan and you finish day 29 and you have 2 weeks to test, it's gonna work okay. But if there's upgrades that you need to make, you have this withholding allowance to do it. It also gives the opportunity to like add a mechanism at competition, right? Maybe you need to add an R or add like a little shindig that's gonna do some task in the game. You can do that there. Practice robots, let's talk about that really quickly. You have some options for practice robots. It doesn't have to be build a whole nother robot from scratch, all right? If you follow my advice and you build the kitbot, which everyone should build the kitbot, right? You can build a second practice robot by just clicking the buy button on AndyMark. It's that easy, all right? You just go to andymark.com, you find the new kitbot, and you click buy one more because you got one in your kit of parts. The second one comes in a week later, boom, there's your practice robot, okay? You don't even have to make 2 full sets of mechanisms. You can literally buy an AndyMark drive base, have 2 identical AndyMark drive kits built, right? Build your entire mechanism on your competition robot. When bag day comes, you take your whole mechanism off, you put it onto your other AndyMark chassis, you put your competition robot in the bag without any mechanisms, or like one mechanism on it. You spend the rest of the next 3 weeks, 4 weeks before your competition tuning your mechanisms on your practice robot. And then as long as your mechanisms are underneath that withholding allowance, you pick up the mechanism off of your practice robot and you bring it to the competition with you and you slap it on your identical drivetrain and you're good to go. It's that easy. You don't have to have CAD. You don't have to have, a detailed design or 3 robots or custom drivetrains. You can have 2 AndyMark drive bases and mechanisms on top and have an effective practice robot, which means that when bag day comes, it doesn't stop your development at all, okay? Along with developing your robot from bag day to your first competition, because if you're not doing that, you're getting behind every day you don't do that. You should also be, just like we talked about in the beginning, keep your head up, keep your eyes up, don't have your head in the sand. Watch what other events are doing. So on 1678, we always do a webcast party. It's like a pancake party. Our mentors make pancakes for the kids. The kids watch matches on the screen from all over the world. Now, we're really lucky these days. Back when I was in high school, we had to open up Windows Media Player, which you may or may not even know what that is, and we had to open up a stream URL, and it was 5 pixels wide by 3 pixels tall, and we had to squint to see a robot, right? Now you have 20 different streams every week in HD on the Blue Alliance, right? And you can watch any of those whenever you want. And you can learn so much from watching other events to see what strategies are working, what mechanisms are working. You can watch things like Fun, First Updates Now. They do a premiere night every year after Stop Build Day where teams make reveal videos. And there's almost hundreds of these reveal videos one night. And you can see so many cool mechanisms, so many cool ideas that your team didn't think of. And maybe you can incorporate some of those ideas now that you have your practice robot with your mechanisms already on it. You can use some of those ideas and upgrade your robot a little bit. Volunteering at events is great. Highly recommend it. If you don't do any volunteering, see if you can have some adults volunteer, some kids volunteer at your events. Look at other robots for ideas. Super, super important. 1678 does this all the time. We have a whole Slack channel like just to steal things from other teams, right? Hey, did you see this team did this? Did you see this picture? Did you see this video they uploaded? And we're taking all these ideas from people posting all around the internet and collecting them to try to get the best information to upgrade our own robots and be competitive. So quick summary, golden rules 1 and 2, keep it simple, steal from the best, invent the rest. For drivetrain, please, please, please build a tank drive. Do not build a swerve. Do not build a mechanism drive. Do not build a swerve drive. Do not build a mechanism drive. Build a tank drive every single year. If it's good enough for 254, it's good enough for you. Don't build anything else. Golden rule number 4, always use rolly grabbers. Touch it and own it. Electrical pneumatics, do a good job early on. Give your electrical team enough time to do a clean wiring job. Golden rule number 5, fail faster. Push yourself to set a very aggressive schedule so you have enough time to fail enough times, because if you don't fail in your shop, you're going to fail on the field. And then competition season, do not stop build season at bag day. Set a pace that you can keep up for the entire competition season so you don't lose out on what other teams are doing to improve throughout the season. One sec. 4 or maybe 5 meetings a week. Yep. Some resources really quick. ChiefDelphi.com is great. Highly recommend you go and even just lurk there and read what other people are posting. And then the Compass Alliance is an effort that some teams, including 1678, have started in the last year. We're aiming for it to be your one-stop resource shop. You can go on there, especially read our pathways. They're on our website. I highly recommend checking it out. TheCompassAlliance.org. Check it out. It's a pretty cool site. So we'll do some questions now. Here's my email and my Instagram if you want to follow me. But before we get to the questions, I just want to hit this up really quick. This is a QR code. If you can scan this QR code now as people are asking questions, it's going to take you to a survey. We'd really appreciate it if you could take that survey now. So if you wouldn't mind grabbing your phones and scanning this QR code now, it'll take you to a survey page. But while people are doing that, let's go to some questions really quick. So yeah, I saw a hand over there. Yeah. Okay, so this presentation, the slides will be uploaded to our website, citruscircuits.org, and the video will be uploaded to YouTube.
Okay, and what is the point of bag day then?
So bag day is, that's a good question. So the point of bag day is it's an artificial limit so that FRC can say they're built in 6 weeks, but it really doesn't serve a function anymore.
Okay.
Great question. Yeah, question in the back. What's the best intake for a tube object? Okay, so a tube, an example of a good tube element, check out 254 from 2011. They had a really good intake for tubes then. We got a lot of people leaving. Interesting. All right, yeah, question.
You stressed the use of sensors in making sure your manipulator's that it stays what it's supposed to be doing. Can you describe some like closed-loop systems that you guys use in the past?
Yeah, that's a great question. So what are some closed loop systems where we've used sensors to accurately position mechanisms? So this year's a good example. We had a motor encoder combo on the elevator, so we knew exactly what height the elevator was at. But then we also had a motor encoder combo on the wrist, so we knew what angle the intake was at. In the past examples, 2017, we had encoders on the shooter to detect speed of the wheels. 2016 was another complicated year. We had a pivoting arm with an elevator on that. Both of those had encoders for positioning. It's pretty much the two things that we call them wrists, right, and elevators. I mean, it's like any pivoting location-based system, like a wrist or an arm, or an elevator, like a linear slide. Those are really the main things for position detection.
So if you don't have a closed-loop system, there's high like probability of collisions.
Yeah, so if you have no closed loop feedback, you don't know where your mechanism is at. The only way you could really gauge it is by watching it on the field, and there's a lot more risk that that robot like mechanisms collide and stuff like that. The other thing that you don't have the advantage of is when you have closed loop, you can do what's called like presets, right? Where like you know that for elevator, for example, you know that this height is a good height to score on the scale, and you can just press a button and go to that preset rather than having to manually adjust it to an exact height and get it right every time manually. You can just press a button and the robot will go to the same height every time. So you not only do you get this feedback and more precise position, but you get the repeatability as well when you have feedback loops in your control system. It's a great question. Yes?
So I remember that you mentioned keeping the robots symmetrical, but
So, I was gonna ask.
Not taking my own advice. No, sorry. Continue your question. I'm sorry.
For that, how do you guys keep your robot from, I guess, like, you know, if you're making a turn, keeping it from flipping to one side in the
Yeah.
middle of the turn, or why did you choose to keep it asymmetrical?
Yeah, so that's a great question. So why, when we're talking about symmetry in robots, why did 6 and 78 make a very odd unsymmetric robot this year? Non-symmetric, I should say. So we really tried to get the symmetric robot working. We tried to do what a lot of other teams did with the forklift off the back, and we just couldn't get it to work in our own prototyping. So we tried to make it where the forks come straight off the back. You have a nice centered robot, but it just wasn't working out for us. And we also knew that we didn't have to pick up 2 other robots. So remember that list of requirements I showed you from 2016? So in 2018, one of the requirements was picks up 1 other robot and climbs with it, right? So it's like we go up and 1 buddy goes up with us. So I've seen a lot. I think 1425, you guys got 2 ramps, right? But you only really ever need to use 1 as long as you have the levitate, right? So it's like we thought through that, and it's good to have the it's cool to have the option, but we didn't really think we needed it. So we figured we only had to lift up 1 other buddy with us. So then, since it wasn't working to pick up off the back just because our prototypes didn't work out, we decided to do the ramp off the side. But yeah, it made a very odd looking robot. It looks more like a cheese grater than a robot. And that's the other thing too, to keep the center of gravity as low as possible and not flip, we made that out of very thin sheet metal because we knew it was going to be high up. We knew it had to be very thin. So that whole ramp only weighs 8 pounds. The whole thing, including the frame members and stuff like that. But we did that because of the center of gravity issues, and we didn't want to be tipping over, which we still did tip over once, but it wasn't because of the ramp. It wasn't mostly because of the ramp. Great questions. Yes, another question.
Something we missed during our season was the ability to shoot a QR robot or behind us. Matt found able to circumvent this with their swerve magic, but it's something we missed. What step in your preseason design or preseason strategic analysis did that come up?
That is a really good question. So in our list of requirements, we had a couple of things. One of our requirements was do a 3-cube autonomous, right? That was something we had written on the board. And to do a 3-cube autonomous, we knew we would have to do that back and forth from the fence to the scale quickly, right? And we quickly figured out, thinking through the times, how long it would take to drive back and forth. We were like, okay, we're not going to have enough time to pick up the cube and then turn around and put it on the scale and turn around and pick up the cube and turn around and put it on the scale. We figured the quickest way is going to be to pick it up and then flip it over our back and shoot it into the scale, and pick it up and shoot it over our back. So one of our requirements was is able to pick up forward, but is able to score on the scale forwards or backwards. And that's how we came up with the wrist that flips over the top. I'll be honest, I was kicking myself too when I saw Poofs, because they not only had that scoring for the scale, but they had that for the switch and for the exchange as well. And it was a huge time saver for them. And it was able to make their robot that much quicker than everybody else. But that was just something that we missed. It's something there when you're really creative about your packaging and your mechanism design. I mean, it's so simple what they did, but it was just a brilliant packaging engineering marvel is really what that robot was. And that's how they were able to get that. So we don't do a great job of it, but things like scoring over our back were decided by our strategic design. Yeah, thanks. That's a great question. Any other questions? We'll maybe do 2 more. Yeah, what do you got?
So I actually was going to ask, so you're saying when you have parts on your robot that extend outside of your brain, you're using the keyboard left, right?
Yep.
So how do you make sure that they're not breaking?
That's a good question. So using thicker material, but you have to think through the whole load case. So not only does your intake have to be robust, but the thing the intake attaches to better be firmly attached to the frame, right? So it's you have to think through the whole chain of when this intake hits a wall, the load's going to pass through all of these things, and I need to make sure all of those things are able to handle that impact, right? So, and honestly, the best way to do it is not think a lot about it. Just make it as robust as you can and then test it. Yeah, and running into a wall is going to tell you all you need to know about how robust it is. If it doesn't break, cool. If it breaks, fix the thing that broke, make it stronger, and then try again. You know what I mean? That's the easiest way to go about that, especially because most of you probably haven't taken finite element analysis or and then you're not doing this complicated simulations on your intake. I don't recommend trying any of that stuff. Just run it into a wall. If it breaks, fix what broke. If it doesn't break, you're good to go. Yeah, that's my advice. Yeah.
What are some
Okay, so there's a great quote by Paul Copioli, one of the great mentors in FIRST. He says, robots break because there's too much material in some places and not enough material in other places. So often things are breaking because teams are aggressively pocketing their tube out, right? They're making these nice like tetrahedral shapes in their frame, and then they run into a wall and it bends along all those pockets, right? So using too thin of material or using too little of it or using aggressive pocketing on things that shouldn't be aggressively pocketed, those are all common mistakes that teams can make. Yeah, great questions. We had one more over here. Yeah.
So what language is the limelight in?
So I do not know the answer to that at all. But they have a website. If you just search up like FIRST Robotics Limelight, you can probably get to their website. And they have a ton of great documentation on there about their product. So you can check it out there. Great question. All right. So if you have more questions, I'm happy to talk. I think we got to end the recording now if it isn't already. But I'm going to be here for a little bit. So let's chat. I'm happy to answer questions. Thanks so much, everybody. I really appreciate the time. Thank you.